Can't guarantee I'm going to answer them all, or be able to, but feel free to interrupt me whenever. So I'm going to talk for, I don't know, half an hour. I might not even be teaching you anything new, but the fun part is after that when we do the download workshop. Okay? Now, again, I don't know if this is all going to be new to you, but again, let's have fun with it. And then we'll download some software and then run some demos to prove that it worked. So just so that I get a sense of the audience here, so I know you guys are from FutureWave. Who works here in WinLab? Oh, virtually everybody. Okay. So everyone who's not professional graduate students? Are you graduate students? Any undergrads here?
No.
Okay.
I think it's all grads.
Okay. So you guys know the score. So, okay, you'll be able to call me on the carpet. All right. So let's get started. All right. So here's a little agenda. I'll run a demo for you to show you something simple that you can do. Talk about the support that we offer in MATLAB and Simulink. Talk about building practical digital receiver. We'll have Q&A at the end, but I really want Q&A all during, and then we'll do the workshop. Okay? And if you have questions, let me know your name. I'm going to try to interact with you by name. Okay? All right. So let's get out of here. Go into MATLAB. Okay. So who knows what this is?
This is Edison.
Nope. No.
Can't see. Anyway.
Okay. Yeah, my eyes are getting worse too. So, anyone know what this is? ADI, Analog Devices, PlutoSDR. Yes, it does. ADALM-PLUTO. So this is meant mostly for an academic audience. The reason that they call it Pluto, I found this out just the other day. The reason that they call it Pluto is because this is not quite a radio, and Pluto is not quite a planet. But you can still do a lot of cool stuff with it. So an RF range from 70 meg to 6 gig, I think a 12 or 14-bit A to D. Very, very good frequency stability. Each LO is factory calibrated, so you got, I don't know, less than 2 ppm of frequency and stability. So for all that capability, how much do you think it costs? $150. We got a guess. All right.
Lower.
It is that. So last night when I did this, we got into a game of The Price is Right. So someone said 100, someone said 101.
47.
No, it's not quite that inexpensive.
94 was the last number I purchased it by.
Okay, so you got a $5 discount. So $99, $100 for this capability. That's really good. I mean, the least expensive Edis radio is $700.
Yep.
And I think that these are kind of comparable in capabilities. So again, it's meant for an academic audience, but we're finding that professionals are getting them too. So, and actually, even also before I go further, the folks who is actually, I guess everyone is doing SDR for this or that. It's all part of the WinLab mission statement. So, okay, we'll just go on. Let's do the demo. All right, so get into MATLAB. So here's what I'll tell you what I'm going to do, and then I'm going to do it. So we're going to start with an image, then transmit the bits using a WLAN compliant waveform. You know, so we use one radio, one laptop, TX antenna, RX antenna. Then we reconstruct the bits at the output and reconstruct the image. Okay, so let's run this. And interestingly, there are times when the demo doesn't work, even though there's just an inch of separation. So we can have some fun with the class and ask, why do you think that's happening? By the way, we are transmitting at 2.4 gig. Okay, that looks pretty good. Oh my goodness, we had a frame check error. Okay, that's the first time that the constellation has looked that good, and we still get a frame check error. If we get any frame check errors, the image doesn't reconstruct. Let's run it again. Okay, that time it did. So, all right, so last night, as I was running, let's try one more time. I don't want to bore you too much, but this will be the last time. Okay, so as I was running this beforehand, there would be some times where the OFDM spectrum didn't look very good, constellation looked cruddy. Why do you think that was happening?
Interference?
Aha! Yeah, I would imagine there's a little bit of Wi-Fi going around the building, right?
There is some.
And this demo isn't doing any carrier sensing, and so it could get clobbered with interference. Okay?
Question, so, but you have this wideband protocol download to the radio, right?
Well, no, it's not downloaded to the radio. We're running the WLAN. We're generating the WLAN signals in MATLAB.
So how about the
And then
one
we're-
layer 2 protocol
what's the
with
none of that, right?
It's
No,
it's
no.
WLAN compliant at the 5.
just the file?
We're not doing any
Okay.
layer 2 and above.
Okay,
So because we're not doing any carrier sensing, we could get clobbered,
okay.
and that is what happens sometimes.
And
Now,
you're probably clobbering me because I can't get a connection.
well, I'm not running it now. Not running it now. I do want to run it one more time, and we're gonna alter things just a little bit. Yep, that's fine. Okay, now just for grins. Okay, remember what this looks like, okay? Now we'll run it one more time.
Oh,
Oh wow, we didn't even get to the constellation. But the spectrum looks positively awful. Okay, so what's going on?
Polarization, orthogonality.
Nice. Very good. So I mean, that's what I'm convinced is going on. And it looks like you've got you're getting some multipath because the spectrum isn't even flat anymore. But you do notice that the power level is way, way low. So it's polarization. I think it is.
Directionality.
but
Yeah.
At home, I tried to move antenna like this. It didn't affect too much of the performance.
Really?
While it's rudderless now.
So, well, it's happening here. What antennas are you using?
I don't know, it's wireless rudder, ASUS wireless rudder with antennas. I try to.
I think here it's one is transmitting, one is receiving.
Yeah.
At home,
Oh,
you
okay.
both antennas are doing the same thing at the same
Okay.
time. There.
Yeah. So anyway, that's some fun right there. Let's go back to the presentation. So, but this gives you just a little bit of an inkling of stuff you can do with the Pluto and MATLAB. And the nice thing about the MATLAB is that it's all open. You can see inside to what all the algorithms are doing. All right. So I'm preaching to the choir here and talking about this, but why do you want to do SDR, MATLAB, and Simulink? Because you want to work with all these standards-based signals. So I guess, Yvonne, you guys are working with Wi-Fi, LTE, 5G, everything,
All of the above.
ADSB.
Everything.
Okay. So, yeah, so a lot of the audiences that I talk to, they don't even know what all these signals are, but that's one of the obvious ways. And you can actually create your receivers in Simulink or MATLAB and then validate them outside the radio. Get them to how you want to be, and the iteration using the software is very, very fast. And so then once you get that software receiver going, then you're positioned to be able to go to hardware. Okay, so now I just want to show you some resources. Again, this is mostly for an academic audience. You might be aware of most of these already. Just to show that there's a body of work being built now that shows professors in particular and students what can be done. So, so these are the hardware platforms that MathWorks supports. So USRP, RTL. Folks familiar with RTL? Okay, good, because that's what we're going to work with in a half hour. Okay, how much do those cost? It's receive only. Frequency range up to about 2.2 gigahertz, 7-bit A to D.
20
Very
bucks.
close, 20. So, for 20 bucks, 3 Starbucks. You get a lot of radio capability. So the zinc, I'm sure you're very familiar with the zinc. That's for, we would use that for HDL targeting. And then the Pluto, which we just talked about. Okay, so if you want to learn more about what MathWorks offers, just Google MATLAB SDR. You come to this landing page where it'll tell you all about the different platforms that we support, loads of examples, white papers. So it's kind of a repository of resources for you. Okay? And then, I love this book. So this was written by a colleague. Are you familiar with that guy?
Mm-hmm.
Okay. So this was written by a colleague out in Scotland. My initial vision of this book was that it was going to be a 30-page lab guide. Once Bob Stewart got finished with it, it was a 600-page tome. But he has 150 different Simulink-based examples, culminating in a QPSK receiver that does all the synchronization. And it's really outstanding. And so if a professor is trying to put together a course, he can cherry pick the examples that he wants so that he can tailor a course for his own purposes. So this book's about 8 or 10 years old, written by people at WPI, focuses on using the USRP. This is the follow-on to that same book. This was written by, mostly by analog devices engineers who are the manufacturers of the Pluto. So this book covers mostly Pluto applications. And again, load of MATLAB and Simulink examples. And it does cover synchronization, which most of your comms textbooks, they're going to say, well, we assume that the signal is synchronized, and synchronization is an exercise left for the reader. But once, as you know, once you introduce the radio, you got to synchronize. Okay, this is a book that's being written now by a professor at Temple, again on the Pluto. This is kind of fun. Again, this is a resource mostly tailored for professors and not for students. But I worked with this professor from Milwaukee School of Engineering, and he built, mostly him, he built this turnkey solution, a whole semester course, say an undergraduate, sophomore, junior level course, that covers starting from analog all the way to OFDM, and it's peppered with SDR labs along the way. So again, don't know if any of you are in that space right now, but I think he did a great job. And he's been doing this at Milwaukee School of Engineering for 3-4 years with great success. So this is available on the MathWorks File Exchange. Who's familiar with the File Exchange? Oh, not so many people. Okay, so small commercial. The File Exchange is a repository of hundreds, maybe thousands, of different uploads from the whole community of users, with utilities, products, you name it. And if you want to know how to do something in MATLAB, odds are that someone has uploaded a submission to the File Exchange. So if you're stuck with this problem and you need to write some MATLAB code to solve it, check this out, because it might have been done for you already. Okay, so just Google MATLAB File Exchange, and you'll get right there. Okay? All right. All right. So again, you may have seen all this already, but you got a perfectly working software radio, but then when you introduce the SDRs, how come things go rotten? So the idea, as probably many of you well know, is to overcome the hardware. So actually, I'm going to put up some pictures, some constellations here, and you tell me what's the imperfection and what do you got to do to fix it. So we'll kind of do a little 360. So noisy front end, that's easy. So what are you gonna do to deal with that? So that 16 QAM constellation is noisy. So how are you gonna deal with that?
Coding?
Just coding, sure. Or even before you get to the baseband, just get as narrow a filter as you can. Filtering is your friend. So IQ imbalance. Do any of the radios that you work with, do they have to deal much with the IQ imbalance, or are they pretty well calibrated?
They have to, yeah, of course.
Okay. How do you guys deal with an IQ imbalance?
Pretty social?
Oh, tell me more. Well, I mean, we've been looking at that.
Yeah.
So memoryless or with memory? Or yeah.
Depends the bandwidth. Yeah, if you have wideband, yeah, you have to deal with dispersion. Yes.
Okay.
Yeah.
So then you're building DPD algorithms?
Used to,
Oh.
not anymore.
Is Future Wave still in that world?
A couple years ago,
Oh.
not now. Yeah,
Because it's a solved problem, or
more or less.
oh,
Yeah.
we'll have to talk afterwards.
Well, that's
I didn't
why-
think it was a solved problem, unless we're starting to
Yeah.
get into IP issues.
Yeah.
Okay. Obviously, phase noise. What might you do there to deal with phase noise?
Get better I/O.
Get better LO,
I've always-
absolutely. If you got nothing better that you can do, you can back off on the modulation type. But generally, you're trying to fill that bandwidth to capacity, so you'll have to learn to deal with the phase noise. Okay, DC offsets. Who here is working with direct conversion architectures? Okay, so do you have to deal with that? With DC offsets?
Yes.
Okay.
Yeah.
And do you do it in software, in hardware?
Software. Yeah.
Okay.
Software in the receiver. Yeah.
Okay. So say on an ARM, or are you doing simulations, or are you building radios?
We did mostly simulations, and of course the algorithms eventually I think got implemented inside ASICs or FPGAs and stuff like that. Yeah.
So a notch filter?
No, you can. Well, it's sort of adaptive, but the effect of it may be a large filter, but
Okay.
Yeah.
All right. So carrier frequency offsets. What do you have? How are you going to deal with that? That's a softball question. What's your receiver architecture got to have if you have a carrier offset?
I mean, some standard protocol provides certain reference symbol. You
Sure.
can use it to some offset estimation and do the computation.
Yep. So, and in this single carrier situation, what did carrier tracking look?
Yeah.
Very straightforward. But you're right, for an OFDM system, the preamble has a particular protocol.
Right, STF and OTF.
Yep, yep, exactly. And then timing skew. And again, for what do you do for a single carrier system if you got timing skew? It's not a trick question, I promise. Throw a simple timing
Yeah, so
in there.
timing sync.
Yeah, well, I mean, Cody's not going to help you that much. Here, I mean, if you've got a constellation looking like that, you're
No,
getting
timing
close to a
is-
0.5 BER. I don't know if any code's going to help you there. So, but anyway, the reason that two reasons that I bring this up is to mention the multiplicity of impairments and corrections that you have to deal with, but also number two is the insights that you gain simply by looking at a constellation. So you can tell immediately, okay, what is my impairment? And then what do I need to do to deal with it? So, okay, and here again, this is just a notional block diagram. Who here has Simulink experience? Anyone? Okay, and what have you done in Simulink?
I built the receiver of Wi-Fi, wireless LAN, and then also ultra wideband. Basically, each module, and I use that to generate the testing vectors.
Ah,
Yeah.
okay. Now, were you going all the way to HDL, or this was
FPGA.
purely simulation?
FPGA, and then it will be used as a testing vector for the PGA, RTL, for the VHDL.
Okay. Yeah. So yeah, you get your test vector in simulation, then you can use the very same one for the hardware.
Input and output. And
Yep, very nice. So the idea is, if what we have advocated to students and professionals alike, anticipate the impairments that you're going to deal with the hardware, model them all in software, and then when you're satisfied that the digital receiver is working, snip out the software channel, put in the radios. Old hat. And then I just wanted to show you that if you have to generate these impairments, MathWorks has capabilities to be able to do that. I'm showing Simulink blocks. We have the same capabilities in MATLAB as well. By the way, quick check. Who here does cons in MATLAB? Okay. Who here does cons in Simulink? So you have.
The comes in.
Who does their work, say, in MATLAB?
Yeah.
Okay. That's okay. I would anticipate most folks, right?
Right.
Again, not a trick question. Who does equivalent work in Simulink?
I think pretty much nobody.
Yeah. So this is about what I encounter everywhere. So not that we don't have a preference for MATLAB or Simulink, because Simulink is actually better than MATLAB for certain operations. But just as I travel, most people use MATLAB. Few use Simulink. Who here has to do RF modeling? Anyone?
Used to do.
Okay. What do you use?
No. Yeah, we don't, well, we just do like everything in baseband impairments like that, like IQ balance.
Oh, okay. So you're not necessarily modeling multi-carrier, all the intermods and harmonics?
No.
Okay. Okay. Because if you are, there is a Comms Toolbox won't do that for you, but there is a product that will work with Comms Toolbox.
In Simulink?
Yeah. Yeah.
What about in MATLAB?
No, not so much. So if you're doing RF modeling, that's one of those places where Simulink is actually a better choice because of the ability to do the multi-carrier simulations. So again, if you have the need. So here's the impairments you can generate, and then if you're going to generate the impairments, you got to be able to correct for them. So we do have canned algorithms for all of these compensations. We are not claiming that we have the absolute best in class implementations, because that's not our mission in life. But we do want to offer you reference implementations that you can use as a baseline, and for I don't know, 80–90% of our code, of our blocks, our functions, our objects, is white box, what we call white box code. It's open MATLAB code that you can go into and inspect and extend and put your own special sauce in if you like. Yeah?
Yeah, I remember this Simulink, once we need to do the clock by clock type of implementation, let's say just like a real FPGA implementation.
Yep.
Then use the Simulink, either
Simulink
as
is
function.
definitely better suited than MATLAB for that. If you have a multi-time domain application, because with MATLAB you have to insert your own time. It's hard to manage time in MATLAB. Much easier in Simulink. Okay. Aha! Come to the end. Questions that haven't already been asked? Okay.
Is there, let's say, I use Simulink that's like 10 years back or 12 years back.
Oh, it's grown since then.
I'm saying, yeah, how is this different from that time?
Well, I don't think the RF product really existed for all practical purposes at that time. Certainly not the multi-carrier implementation. Let's see. There was an HDL coder product that you start with a Simulink model and then you can automatically generate HDL code. That product did exist, but it was pretty immature.
Yes, I was gonna. That's my experience with the
Yeah.
coder last
Yeah.
time I tried it.
So after 10 years, I can tell you quantitatively it's better. I'm not super equipped to tell you all the reasons why it's better, but there is more functionality that's covered. Certainly, and then I think it's better integrated with Vivado, Xilinx. But the idea of the product is to generate non-vendor specific HDL, so you don't have to lock yourself into Xilinx, unlike say with System Generator. So does that make sense?
Yeah, I even remember a long time ago I played with even MATLAB to HDL converter.
Yeah.
So that was more than 10 years ago, but
I didn't think
is
we
there
had-
something still?
So we can generate HDL from MATLAB, but we don't really advise people to do that anymore because we
Okay.
realized when you're doing fixed point modeling, Simulink is a much better platform to see what's going on, because with MATLAB, you look at a variable and you have to hover over it to see what the data type is. It's pretty cumbersome. Whereas with Simulink, you can tell immediately, that's a UN32, or that's a UFix15 EN4. So it's much easier to do the fixed point modeling in Simulink, and we've built a lot of tools for that fixed point modeling in Simulink. So again, if you're doing so actually you've hit upon 2 of the 3 use cases that I think Simulink is actually superior. So RF modeling, going to HDL, and so these are kind of advanced applications. And surprisingly, if you're a newbie and you just want to throw something together really quick, a modulator, a channel, a DMOD, and then an error rate calculator, wow, super simple in Simulink. So if you're very much a newbie, or if you're very advanced, I think Simulink has a lot of advantages. Everything in between, it seems like MATLAB has the edge.
Can you just flip back to the picture where you're showing the RF block set?
Oh, actually, I wasn't showing any of the RF block set.
Oh, okay, because for RF modeling, you mentioned something, right?
This?
Yeah, this
Okay.
impairment.
Right. So all that stuff is in Com's Toolbox.
Oh, okay. So those are Com's toolbox, not necessarily Simulink block sets.
Well, I try not to create these product boundaries and product silos when I talk about this. But since you ask, yeah, these are all in Com's Toolbox. But they don't perform, shall I say, proper RF modeling. For example, let's see here. No, let me go up. Okay, we've got a memoryless nonlinearity.
Oh, okay.
For many applications, that's okay.
Yeah.
But if you really want to do a high fidelity model, you want a PA with memory.
That's right.
So that guy comes with the RF block set. In fact, it's one of the crown jewels of the product. So it depends. If you want to do a coarse grain modeling, this is sufficient. But if you really need to include memory, then you're going to go to RF block set. Okay?
So inside the RF block set, you have a full complete predistortion module, or you can build a fully complete.
Interesting you mentioned that. Let me go
You
forward
can
again.
build your own block, right?
Yeah, you can always expand.
Oh dear. Shoot. Nope. Okay. It does turn out that Com's Toolbox ships a predistortion block.
Okay.
Because since that operation is typically done digitally,
Right.
it felt like it had a better home in the Com's Toolbox than the RF block set.
I see. Okay.
So the capability is there, you just need both products. And we have some examples, some demos that use them and show, say for a 16 QAM system, the improvement in EVM. So I guess your metric of evaluation is EVM?
Oh, spectrum emission.
Yeah.
Yeah.
So we, like I say, we have an example that shows that. If you were to Google on the web, digital predistortion Simulink, I'll bet you'd come upon it quickly enough.
Yeah.
Okay. But we're by no means done with our investment in DPD. We're interested in deep learning algorithms. We're interested in actually talking to hardware. So we've done some partnering recently with National Instruments, where we use some of their test gear to measure and compensate for the PA from a Wolfspeed device. So there's some YouTube videos towards that effect. So great questions. Anything else?